Hey physics students, going to give you some notes here about friction. You know what friction is. It's been part of your lives from the very beginning, right? So friction is the sort of the grip, if you want to think about it that way, between two surfaces. Whether you're talking about something that's like sliding across a surface, it's experiencing some friction. If there was no friction and there was a constant force this way, then that would accelerate it, right? So if something's like sliding at a constant velocity, well, we've made that force diagram before. That'd be like force up, support force, force down of gravity, force of push, and then a friction force. And we know that the force of the push and the friction force would have to be equal if it's sliding at a constant velocity. So how do we actually like get into like making equations and mathematical models for friction? There's lab exercises that you can do, and I've tried all sorts of things, and nothing ever goes particularly well because friction is just messy, and there's no way around that. So I decided for us that we're going to skip doing a lab activity about friction, and I am just going to let you know what is the mathematical model that we're going to use. So what do you think friction depends on? Well, friction depends on how much contact there is between the two surfaces, right? The harder that they push together, the more friction there's going to be. If you think about, here's a good example. Let's make a little sketch for you here. On the back of this already used piece of paper. If you imagine like a mountain, not a mountain climber, a rock climber, who's like in between, like kind of wedged in here with pushing feet up against this, and then maybe like pushing backwards here. That's a pretty terrible diagram there, or picture of this person. Anyway, you get the idea. They're kind of in between these two rock walls. Maybe you've even done this or something kind of similar to this. What that person needs to do is they need to push real hard with their feet against here and with their hands / back against here. If they don't push hard enough, then they're going to slip and fall down. What are they accomplishing by pushing hard? Well, the harder that they push, the more pressure, the more contact they can generate between their feet, their hands back, and these rock walls, the more friction there is. So it's not like there's just like, oh, here's a surface, like here's like rock climbing shoes, and here's a rock. So there's like some amount of friction force, and that's the end of it. It depends on how much pushing there is. And what force is it that describes how much pushing there is, how much contact there is between two surfaces? That's the normal force, the support force. So here is our friction equation. This is what you've been waiting for. The force of friction is equal to this, what we're going to call, that is a Greek lowercase mu. It looks like sort of a cursive U, but it's got this like long front edge on it. Mu, mu is the name of that letter, times the normal force. That's it. And this mu is the coefficient of friction. Most of the time, the most common type of problem that we're going to look at, you're going to be given that number. What kind of number should we expect there? It's usually between 0 and 1. You really think of it as like a percentage. It's like if it was 0.5, it means how much friction do you get? Well, you get half of whatever the normal force is. and you can't get more friction than what the normal force is, at least not without a lot of engineering and trouble. It doesn't naturally happen that way. So coefficient of friction between 0 and 1, and that number, that coefficient of friction, has no units. It's the first example that we have seen, and maybe, trying to think, maybe the only one that we're going to see of a physics constant that is that does not have any units. Why does it have no units? Well, it is like just a ratio. If you think about the units of this equation, the friction force, that's measured in newtons. The normal force, that's measured in newtons. So what's this? It's just like a scaling factor. It tells you how much of the normal force is going to show up as friction. All right, so it's just a number. All right. So I think that I would like to do a couple examples for you. And that'll help you get started on the friction problems that I'm going to ask you to do. So here's an example. Let's say we have a box that is 10 kilograms, and let's say it's being pushed by a force of how about 100 newtons, and it's being pushed across a rough floor, and the coefficient of friction is 0.3. Right? You can expect that to be a number between 0 and 1. And what are we going to try to do? We're going to make a force diagram and then find the acceleration of the box. Okay, so let's see. Let's try to make that force diagram. It's not a super complicated force diagram. There's no ramp or hill or anything like that, so I'm going to make my axes just like a regular old XY axis, and no forces at any angles at all, so I'm not going to have to do any sine and cosine stuff here. Start out with my gravitational force. That's going to be 10 kilograms times 10 gives me 100 newtons. I also know that there's 100 newtons of push, and there must be, because there's no motion in the up-down direction, I know that this and this must be equal to each other. I'm not going to put a little tick mark on this one. This is also 100, but it's not balancing. This is to the right and this is down, so those can't balance each other. Up-down can. So that's my support force. That's got to be 100 newtons. Okay, how much friction is there? Well, this is where we use our fancy new friction equation. So the force of friction is equal to mu times the normal force. And here, mu is 0.3, and the normal force is 100. So that is 30 newtons. Right? And now we can find the acceleration, because I know that that unbalanced force is equal to mass times acceleration. So the unbalanced force, actually I think I want to write it like, try to be consistent with the way I've written it in other solution videos for you. So the unbalanced force here, the up-down, of course, that balances. There's no motion in the up-down direction. I have this push is on the winning side minus friction. So force push minus force friction. Unbalanced force is winner minus loser. So unbalanced force is mass times acceleration. and the pushing force is 100. The friction force is 30. So the acceleration, 100 minus 30 is 70 divided by 10 is 7 meters per second squared. Well, there's a friction problem done for you. I think I'll do 2 more examples. Let's see, how about, here's a similar problem. How about that same box, 10 kilograms, but this time it's being pulled by another 100 Newton force. But that 100 Newton force is at a 20-degree angle measured from the horizontal, like that. And it's being pulled at a constant velocity. What does that mean? That means the forces are balanced. What we want to do, we're going to, of course, we're going to make a force diagram. And then we're going to do fully quantitative, meaning all the forces, all the components, everything in the diagram will be labeled with numbers. And then in the end, we're going to use the information that we have there to find if this is going at a constant velocity, then what does that coefficient of friction have to be? Find that mu. Okay, so, and if you think about that, if you're like, well, geez, I've never done that before, Mr. McGrath, I don't know how to find a mu. Well, think about our friction equation. The force of friction is equal to mu times the normal force. So if I can make a force diagram where I know how much friction there has to be and I know how much support or normal force there has to be, then I can solve for that. So that's our goal. There's no ramp here. There is a force that's at an angle, but I am not, when I'm making that decision about how to set up my axes, my dotted lines here, you're going to look at the surface, not whether there's a force that's at an angle. Is this surface at an angle? No. So that means we just have regular old ups and downs. Okay. I'm going to start with my gravitational force, mass times 10. Okay, I've got this pulling force, which is also 100 newtons. And that, because according to the way that I have drawn my axes, this is going off into one of the quadrants. So that means I need to break it up into the x, just like I'm plotting a point, and y components. It is important that you put the arrowheads on the ends of these, that you're going this way and then this way. How do you get from here to here? You can go this way, arrow, and this way, arrow. It's really important because we need to see that ups and downs balance and lefts and rights balance. So please don't leave those out. This is a 20-degree angle. I'm going to go ahead and right now grab my calculator and make sure that I'm in degree mode, and then I'm going to find the two components of this. This side right here is adjacent to the 20-degree angle. So to find that, I need to do 100 times the cosine of 20. That's about, I'm going to call that 94, I'll round to the nearest Newton, and then 100 times the sine of 20 will give me this. Call that 34 newtons. Okay? Looks about right. Okay, now what other forces do I have in this diagram? I know that the forces are balanced. Now, to balance in the up direction, we have that support or the normal force. How big will it be? Will it be 100 newtons to balance force of gravity? No. Why not? Because there's also an upward part of this. So I want you to look at the diagram. This is why the arrowheads are so important. What we know, since the forces are balanced, that all of the ups must balance all of the downs. Now there's only one down, but there are two ups. So between these two, right here, we have to balance this. You can write out an equation if you want there, but I'm hoping that you can just see that that means these two have to add up to this. So that has to be 66, right? Because 66 plus 34 equals 100. So where do I make my little tick marks? You don't, because I have two different things adding up to this one. So I don't have a way of indicating that. Of course, I can write the numbers in. Now I can see that those are balanced. All right. How much friction is there? Well, in the left-right direction, left and right has to balance also. So I only have this going to the right. This is the only thing going to the right, and this is the only thing going to the left. So they have to balance each other. That's the only way that can happen. And now I'm good. My left and my right, if you want to make little marks, you could do it on those, right? Because there's only one here, one here. So left and right are balanced. Up and down are balanced. That force diagram is done. And now we just have force of friction is equal to mu times the normal force. The force of friction is 94. The normal force is 66. Uh-oh. Well, I got a mu that's bigger than, I'm pausing because I don't like the mu that I got. So, yeah, oh well. I just picked bad numbers there, I guess. So in this case, we're going to get a mu of 94 divided by 66, 1.42. That is just very unrealistic. What is that telling us? It's telling us I should have been a little bit smarter when I was picking the numbers here. I think I should have made this smaller. The problem here is that if you really were pulling with this much force on this box, you're not going to be going at a constant velocity. It would accelerate. So I should have picked a smaller number there. But anyway, if you do the math here, that is what we get. So unlikely that you're going to see a lot of problems where the mu comes out to be bigger than 1. But that is the correct answer according to the way that I set that up. All right, one more. This time we've got, should we stick with the same box? This box is getting a workout. The same 10 kilogram box. Now it's on a ramp, and the coefficient of friction is, let's say it's 0.18, and let's say this ramp is at 30 degrees. And we want to find the acceleration of the box. Okay, so I'm going to make a force diagram, because that's what you do. This is on a ramp, so that means that I'm going to tilt my paper to the side so that looks like it's horizontal, and then I'm going to make a dotted line straight across. Looks like straight across now. And I'm going to make another axis perpendicular to that. Use a ruler for this if you like. Okay. And then just for a minute, I'm going to go back to this orientation, because I would like to now drop the force of gravity straight down. Force of gravity is equal to, it's the same box, 10 times 10, that's 100 newtons. Okay? And now everything else I draw in the diagram is going to be in line with these axes. So I'm going to go ahead and tilt back now. Okay. First thing I'm going to do is I'm going to take this force of gravity and I'm going to break it up into its x, y components. Why am I going to break up the force of gravity? Because that's what we do every single time we have something that's on a ramp. Make the arrow at the end, that's important. And there. Okay? Where is the 30-degree angle in this triangle? Well, if you drew your diagram at all to scale, it's down here. And the next thing I'm going to do, since I'm working in this triangle, I'm going to finish what I started here. I'm going to do 100 times the sine and cosine of 30. 100 times the cosine of 30 is about, I'll call that 87 newtons. Now, which side is that? That's adjacent. Cosine is adjacent to the 30, so that's the one here that's touching that 30-degree angle. That is 87 newtons. And then 100 times the sine of 30 is going to be 50, because the sine of 30 is a half, and that's this. Right? Okay. Now, there's nobody pushing or pulling on this, so there's not like another force. There isn't like a force of motion or force down the ramp. This is the part of gravity that's making it slide down the ramp. There isn't something else there. There is a support force, and there's no motion of this box in this direction. It's sliding down the ramp this way. So that means the up-down forces must be balanced. And up-down for us means this is up and this is down. So those must be balanced. And we're assuming that it's accelerating down the ramp, and we know what the mu is. So how much friction? Is the friction going to balance this? We don't think that it is. We think that it's not going to be big, so I'm going to try to draw it nice and small there. How much friction is there? Well, time to use our fancy new friction equation. Force of friction is equal to mu times the normal force. So force of friction is equal to mu times the normal force. So I'll call that 16 newtons. Okay, my force diagram is complete. Now, what's the unbalanced force here? Well, in the direction of motion, to this direction, I have this winning versus this losing. What is this? Like, how would I write this in this equation if I wanted to write kind of like what I did here, if I just want to write the equation, the unbalanced force equation with the names of the forces? Well, this right here is the force of gravity. It's one of the pieces. It's the sine component of that. It's the opposite. So I'm going to write it like that, minus the force of friction. That's my unbalanced force equation. Force unbalanced is winner minus loser over here. Okay? Unbalanced force is equal to mass times acceleration. And that force of gravity times sine of 30, that's 50. minus the force of friction is 16. So 50 minus 16 is 34 divided by 10, so that's going to be 3.4 meters per second squared. And that's how you add a little bit of modeling for friction into what we already know. So that is the big equation, the big new piece of information right now. Do you still need to make force diagrams? You betcha. All right. Good luck with the problems. See you later.